Welcome! In this video, we're going to talk about microcontrollers in the big picture. So the idea in this video is to introduce you to some high-level concepts about microcontrollers and what they do. And using this information, you'll be, I think, a little bit better able to kind of pick a microcontroller for a project and not be so scared of maybe a project and how big it may be. Because at the end of the day, microcontrollers are fairly simple in what they do, but it's really easy to get bogged down in the details. So on the left-hand side, we have a picture of a Blendtec blender. On the right, here we have Lightning McQueen. So what in the world does Lightning McQueen have to do with a Blendtec blender? Well, from the perspective of a microcontroller, quite a bit. So kind of looking from a distance here, we have a microcontroller in the middle, and the microcontroller almost always kind of just does a few things. The first thing it needs to do is it senses something from the outside world. This could be a button, maybe some sort of sensor like a light intensity sensor, it could be sound, but we're going to sense or measure something. Using that data, it may control something else, like a screen, a motor, any other thing that you have to provide an input and control it to make it work. Kind of lastly, there's always an element of communication. So what does that mean? Well, what are we communicating with? I don't know, another microcontroller, a PC, maybe a cell phone. So the microcontroller may report what it's doing or maybe get a command from something else about what it's supposed to do. So another way to think of a microcontroller is it's kind of like a big bottle of glue. Oftentimes, you kind of have the pieces around the ends, meaning you have a sensor picked out, maybe you want to control a motor, you want to talk to it with a cell phone, but you need something to piece together, and that's where the microcontroller comes in. It's just glue. Now, an important point about microcontrollers, it's all about the I/O in the software you write to control it. All right? So you just have to understand your I/O, and then once you understand all your pieces, you could then come up with a strategy to figure out how you're going to control this system. So what do you have to work with in a microcontroller? So we're going to first talk about digital I/O. When we think digital, we think of two states, on and off. So in a microcontroller, we can have digital inputs and we can have digital outputs. And almost always, the digital I/O can either be 0 volts or some supply voltage. Like, for example, a lot of microcontrollers are 3.3 volts. Same thing with the outputs. We have 0 and 3.3 or 5. And so by using software, we can have a digital I/O kind of turn on an output or turn it off. And by playing around with the software, we can make create special timings. We can make little pulses. We can almost do whatever we want. Our only limitation here, is that the microcontroller takes a finite amount of time to read an input or control an output. So, always think about this. Microcontrollers, we read inputs and we write to outputs. It's as simple as that. Now, how you actually do that in code, well, we're going to look at that in another video. But think about this. We read an input and we write an output. So, digital inputs, all right, a big red happy button to destroy the world. That can be an input we want to read from the switch. Vice versa, if we want to control, maybe the digital output will control a light bulb, or it'll control the trigger to a nuclear weapon. I don't know, whatever you want it to be. So, two simple cases of input and output, and that's a very common place to start, our switches and LEDs. But don't limit yourself to those I/O. Think of any input-output that can have two states. You could be controlling a large motor on and off, very large lighting, the sky's the limit. Now, an important thing to understand is that these I/O pins, this I/O on the microcontroller, are physical pins on the chip. You can write software to manually, I'm going to use the word twiddle, to turn or twiddle them on and off. Now, it's also the case where oftentimes digital I/O pins are connected to internal peripherals on your microcontroller. So what does that mean? That there's special hardware that can twiddle the I/O in a special way, so you don't have to necessarily write software to do it. Now, a good example are, for example, communications interface, like a UART, a serial port, SPI. We can get more advanced, like Ethernet or USB. Those are kind of like digital I/O, but the timing is can be kind of precise. We don't necessarily want to write software to manually turn on and off I/O to do that. We could have hardware that'll do it for us. So what we do instead of toggling digital I/O pins, maybe our microcontroller is hardware that can do it for us. Likewise, there are certain times where we have high-speed signals, digital I/O we want, and that we could write software over and over again to maybe sit in a loop and to read a signal or to write a signal. But almost all microcontrollers have that covered for us. They have special timing hardware that can do this for us. So, for example, input capture. Sometimes we want to capture, let me draw an I/O. Let's say we have a sensor that generates a 0 and a 1, and we want to capture this time. Well, a good way to do that is what's called an input capture peripheral. So what an input capture peripheral would do is kind of detect this transition and maybe this one and kind of give you a count in between. Now, on the output side of this, we have things called output compare that kind of do the same thing, where they'll compare maybe a number against a counter and toggle I/O when they match or when they're different. And using that, we can get more complex functions such as pulse width modulation, or PWM. Now, if you don't know what that is, now is a good time to look it up. So I'll tell you in a nutshell. For example, it's very common when you're controlling servos and motors, you have to generate pulses that they're on for a certain amount of time and off. And the ratio of this on time to this off time needs to be controlled, and we call that pulse width modulation, where we're not necessarily controlling the frequency, meaning the time between rising edges. We're just controlling this width here with respect to this width. Now, and it's harder to do it. Now, there's nothing stopping you from writing software to manually toggle pins, but a lot of times we have peripherals to do it. Now, microcontrollers have other internal stuff to drive I/O. I can't go over it all, but it depends on your microcontroller. But there's other internal stuff. But always keep in mind that if you need to do something precise, there's always hardware to do it for us, or we could kind of do it ourselves. Now, what about, that covers digital. Now, what about analog? All right. So what if we have to generate a range of output voltages? Well, on a microcontroller, we have the concept of a digital to analog converter. What you do is digital analog converters, they have a certain range we work over. So we're going to say it starts at 0 and ends up at some reference voltage. And, you know, in this case, maybe I'll say it's 3,3. And then we can hit any number of steps in between, where the number of steps in between is, we call that resolution. So let me draw like a, you know, an example here. So let me draw little axes. And I'll draw over here as T for time. And we'll say this is volts. And so what a DAC can do is you can kind of control it by writing values to a DAC register to control its output voltage. And what you do is this, over time you change it, you can create waveforms. So maybe you want to drive a speaker. You could use a DAC to do that. Or maybe you have some other little widget that needs analog control. You do it with a digital to analog converter. And the faster you output, that's called the sample rate, kind of the the higher frequency waves you can make and the more precise it can be. And so DACs, the only thing you got to worry about now is that they can kind of generate a voltage from 0 to something. You can wire up the circuit to go negative with some usually external components, but you're not limited to that. And then all you do is you change that value over time to maybe have a set point, to maybe generate a waveform to drive a speaker, or maybe you don't. Maybe you just leave it at some value. Now, here's the other way of going at it, is what if you need to measure something? So we have what are called analog to digital converters. They kind of do the opposite. They can take a certain range and say it's 0 to some reference, and this may be 3.3 volts, and it has a certain number of steps it can look, but it can kind of come up with a digital code that represents this, the amplitude of your signal. So once again, what I'm going to do is I'm going to draw T for time. I'll just write capital A for amplitude. And let's say we had a sensor, maybe this is a light sensor, and this is showing light intensity. Well, what a digital to analog converter can do, it has a certain resolution, and what that means, it can kind of see certain discrete steps. Let me just draw the steps here. And that is completely dependent on how many steps is dependent on kind of the quality of the analog digital converter. And what's in your microcontroller. But when you read the A to D converter, it always returns you, a number that is one of these steps, where here is 0, and this would be 1, 1, 2, 3, 4, 5, so on and so forth. And it'll just return a number that's proportional to this waveform. All right? And then all you have to do is kind of convert that number, once you know the reference voltage, back into what it is. Now, oftentimes, the microcontroller has a somewhat small range of what it measures. It's almost always 0 to some reference voltage. If you want higher or lower voltages, you have to design an external circuit to kind of map that external voltage into the signal range of the ADC. But that'll be a topic for another video. But what I want you to take away here is that if you have like some sort of analog signal, say from a sensor, we would wire it up to an analog to digital converter, and almost all microcontrollers have these built in. Now, here's a little anecdote, is that more often than not, analog to digital converters have, microcontrollers will have an analog to converter or digital converter built in, but not quite as many have a DAC. It's more common to see the other way around. Now, there's nothing stopping you from buying a DAC and hooking it up, and you can also, and we're going to look at another video, if you can use PWM and a filter to generate, an analog waveform. But so that ADCs, analog digital converters, and DACs, digital analog converters, kind of will allow us to interface with the external world. Now, lastly, we have the concept of an analog comparator. So you can buy analog comparators or use an operational amplifier, and they simply ask a question. Is one signal greater than the other? In almost all cases, the 0 volts to some analog supply, say 3.3 volt, is the biggest signal. That's the range. But it'll just work in such a way that if a signal's if the plus terminal is greater than the negative terminal, it's high. If not, it drops low and goes from there. So you can use that for doing certain compare operations. Now, not all chips have this built in. Not all microcontrollers will have that as a feature, but some do. So that's useful to know. So the question now that you know we have digital I/O and analog I/O, how do I interface my widget, whatever that may be, to a microcontroller? And there is a lot of questions about this. If you look in a discussion forum, how do I hook up this LCD to a microcontroller? Well, here's how you do it. You don't have to ask anyone else. You can figure it out yourself. So here is the first thing you need to do, is you have to absolutely understand the interface to your widget. So I'm going to underline the interface to your widget. Now there's two sides of this, both the logical and electrical. By electrical, you've got to understand, does it need 5 volts? Does it need 3.3 volts? Is it analog? Is it digital? You've got to understand that. And not only that, you have to understand, does it need a serial port? Does it need 8 data bits? Does it need 8 control lines or 6? You've got to understand that as well. And lastly, you've got to program the thing. Sometimes some widgets have a microcontroller built in. It has some of their software it's running. You have to understand its interface. And how do you understand it? Well, you've got to read. 99% of engineering is reading. You've got to understand, these products or these widgets to be able to control them. If you don't take the time to read all of the data sheets and application notes, there is no way you're going to be able to hook it up, without having problems. So the next step, let's say you understand your widget. What I like to do is say, is there an internal peripheral, meaning a serial port, SPI, whatever, that can automate the interface? So for example, I might have a chip, let's say a sensor that has an I2C interface. If you don't know what I2C is, now is a good time. I'll just write it, I2C. You could certainly just twiddle I/O pins to make it happen, but a lot of microcontrollers have that built in. So you want to figure out, what does your microcontroller already have that you can use? That way you're not using all of your processing power, all of the microcontroller to control one interface or one widget. Now, here's something I say, consider bit banging digital I/O. And what's bit banging? That means manually toggling pins in software to kind of get the correct waveform. So you would literally write code to say set pin high, set pin low, set pin high, wait, set pin low. You can certainly do that. And if your microcontroller is fast enough, you can do it. But it's often, you only do that when you have to. Because you want maybe your microcontroller doing something else or going into a sleep mode. And so my rule is, first look at all the internal peripherals that you might have to automate the interface. And if you don't have that, then think about how do you bit bang the interface. Now, it's important to note that your widget may require a combination of both. You may have some of the interface, it might have a serial port and some digital I/O, and you have to maybe mix and match a couple different things. Now, you might ask, well, how in the world can I know? Well, the reason you can know is that you have to read the data sheet for your widget. And if your widget doesn't have a data sheet, find a widget that does. You have to understand the interface or you'll spend a long time playing around, because these things can be kind of complex. All right, so the last step is then you write firmware that commands the internal peripherals and twiddles the I/O in a way that kind of conforms to the interface of your widget. So if your widget needs 10 data lines and they have to toggle at a certain rate, you have to write software, it's actual code that'll move those I/O pins or command the internal interfaces to make it happen. All right, so once you understand this process, nothing's off limits. You'll never need someone else to say, write the interface for you. It's really not that hard. The key is you have to take the time to understand the interface. Now, I'll admit, I'll use library code or someone else's code, maybe to to get something working, but I always take the time to understand both sides of it. You know, I liken it to plumbing. You could go to a hardware store, you know, and buy every fixture there is and hope that you're going to plumb your house. But if you don't understand your fixtures, meaning say your hot water tank or your sink and what they need, you're going to end up wasting a lot of time and effort just kind of buying materials. Now, let's look at a simple widget. Here I have a Blendtec blender, and, you know, a blender's a great widget. So we can see here a blender, it needs a motor. We have some buttons, and we have kind of this display. So this is kind of maybe our communication to the user, but it's some I/O. So that's some good digital I/O right here. This is some digital I/O. And this motor is probably controlled by PWM. And there may be other things in there to do speed control, you know, and maybe have temperature sensors, you know, to see if the motor is getting too hot. So we have here our Acme Mark I, you know, our generic microcontroller. So the buttons, that would be just digital inputs. I'll just say digital DI. Now then, it also has to control the screen. All right. This may be a serial port, you know, so we'll say UART. Now, if you don't know what UART means, the great part about Google is you can just search for it. It's a serial port. Maybe it takes a serial port. We use that for the microcontroller. And lastly, this widget, someone has to control the motor. So we may use something like a PWM, pulse width modulation, to control what's called an H-bridge for the motor for this blender. And once you understand kind of the I/O of your widget, you just write the code that would say talk to the screen, read the buttons, and control the motor. And the kind of quality of the product then is kind of defined by the quality of the software used to you know, implement these interfaces, because you want, you know, the buttons to respond fast, and you want the screen easy to read. Maybe you want the motor to ramp up and ramp down nicely in speed, so on and so forth. Now, let's look at Lightning McQueen. So what does this have to do with the blender? Well, everything. Lightning McQueen is just a more complex widget. Here is the big difference, is that the blender may have one small, say, 8-bit microcontroller. Lightning McQueen, he may have up to 60 MCUs or microcontrollers. And you'd be like, why in the world would you need 60 microcontrollers? Well, cars are very complex. And to deal with the complexity, they distribute intelligence throughout the car. So let's say we have our Acme Mark I, and we have a bunch of like Acme Mark II processors. The Mark I might be a really fancy processor. So what would that do? We'll just draw him in here. He might be the engine control unit. He's controlling all of the timing, all of the, you know, timing of the fuel injectors, watching the brake systems. Well, the engine control unit needs sensors. So we may have a sensor suite, you know, in our car from the Mark II. Say a mass airflow sensor, you know, measure speed sensors on the wheel. We may have tire pressure monitoring sensors built into the wheels. We may have, you know, sensors on the dash, you know, or just temperature sensors kind of distributed through the cabin. We may have a whole Acme Mark II dedicated to climate control. And we'll say climate control. Say the temperature, regulating the, you know, temperature of the cabin. And the big difference now in a product like this is that all of these microcontrollers, and I'm just going to draw a line like this. Let me draw some arrows. They will have to communicate over a large bus. Now, for example, in automotive, a very popular bus, because it's very robust, is called CAN bus, Controller Area Network. It's a neat bus that's made of 2 wires that you can send little packets or messages of data between a bunch of different nodes. And the way a car works is you just have a lot of these microcontrollers distributed out throughout the car for all the different functions, and they all kind of talk on one or more, say, a CAN bus. So your widget may be something like this. Don't be afraid to use more than one processor, because sometimes it's easier to think about, well, let's distribute the problem and have multiple processors attacking the problem. So that's an idea. That's an example of a more complex widget, but it's really the same thing as the simple widget, the Blendtec, in that it's just a microcontroller controlling I/O. The big difference is that there's just more I/O. So a lot of the difference between, say, the Mark I and the Mark II, maybe this is a processor running at 200 megahertz, and he is, I don't know, 32-bit. This may be, say, for this mass airflow sensor, he may be an 8-bit microcontroller, I don't know, running at 10 megahertz. So what we do is we just distribute the problem, we distribute, our solution to the problem around the car. So that's a good example of, a larger widget. Now, your project may fall somewhere in between, but at the end of the day, it's just I/O. Now, in the next videos, we're going to kind of dive in a little deeper to see what's in the microcontroller and kind of how do we pick a microcontroller. Because there are literally tens of thousands of different variants, and it can be a little overwhelming. So I hope this video was useful. Tune in again for more getting started with microcontrollers.